But I'm going to make this fairly easy on you without too much math to put you to sleep, and I'll try and give you a little bit of an overview of what we do when we look at atmospheric pollution from satellites. And I'll try and impart, if I can, why we think this is exciting and interesting and maybe something you might want to do later on in your careers. So, first of all, I'd like to thank Dr. June Kim and everybody in the GEMS team and Yonsei University for inviting me here. It's a great pleasure to be here. If my voice gives out this afternoon, it's Professor Kim's fault for taking us to sing karaoke last night, and I'm suffering a little bit from it. I can feel my voice going, so you can blame your professor if I can't finish the end of this lecture. Okay, so in this talk I'm going to give a very quick overview of a lot of different things in tropospheric remote sensing. I'll start just a little bit about tropospheric remote sensing of pollutants. I'll give a few of the examples of some of the pollutants that we can retrieve from space. I'll talk about some of the emission sources and also the transport of these pollutants around the globe. And I'll talk a little bit about something that my group particularly has been working on a lot, and that's improving the retrieval vertical sensitivity. That gives us a little bit more information about what the concentrations of pollutants are down near the surface where they affect our air quality. And then I'll talk about trends and validations of some of the long-term records that we've got from satellites these days. And at the end, if I have time, which I probably won't have, I'll talk about going from LEO orbit to geostationary orbit, like GEMS, and why we might want to do this. So what determines our air quality? This is just some basic list of the different things that are considered pollutants by the Environmental Protection Agency in the USA. These include sulfur dioxide, which comes out of a lot of coal burning and things like that. Nitrogen oxides, which you'll, I'm sure, hear a lot about this afternoon. Carbon monoxide, CO, which is, I think, a gas that I've spent a lot of time working on. Particulate matter. Particulate matter at 10 microns and smaller, and 2.5 microns and smaller. That might come from smoke and dust and fires and things like that. And then there's things like lead from industry and transport and other toxic metals like persistent organic compounds in the atmosphere, etc. Then we have what we call secondary pollutants. These are things that are produced by chemical reactions in the atmosphere. And that includes ground-level ozone, which is often caused, it could be a mix of these nitrogen oxides, and CO, for instance, would give us ground-level ozone, and also some of this particulate matter here. For instance, we can have oxidation of the sulfur dioxide here to form sulfate aerosols. So this is a quick overview of some of the things that we're interested in measuring, if we can, from space. So I'll give you a quick overview of tropospheric remote sensing and how we do this. It's a relatively new area of study. It's been, in the scheme of things, it's been going on for about a decade or so, going on 2 decades perhaps. And we've got a lot of nice measurements now from low Earth orbit observations from different satellites that will go around the Earth in polar orbits. And Dr. Levelt will talk about one of those, OMI, in the talk after this. And so we can observe columns and partial columns, and sometimes we can even measure something about the distribution in the vertical of some of these different compounds I've talked about before. There are 2 different views. If we want to look down towards the surface of the Earth, then there are 2 different views we can take from satellite. We can go to geostationary orbit, like GEMS will do, and sit at about 36,000 kilometers above the Earth's surface and look all the way down. This gives us a regional view of what's happening, and we would need several different geos, one after the other, parked at different positions around the equator in order to give us a global view of what's going on. It is actually a geostationary orbit. It's at this altitude here because that's where you need to be for your orbit, to be going around the equator at the same rate as the Earth's turning. So that's why we sit and we stare down at a particular spot on the Earth. And then we have polar orbits, which are much lower down in the atmosphere, at 700 to 800 kilometers or thereabouts. And they give out swaths like this. Usually it takes the satellite somewhere in the region of about 100 minutes to go around the Earth. And as it goes round, often it'll scan from side to side, and that's why we have these nice wide swaths here. If it didn't go from side to side, if it just we just considered the suborbit track of the satellite, it would take about 16 days or so to get back to the same place after making one measurement to get back to that same place again. Okay, so how do we do remote sensing? There are two things. Well, when it comes down to looking at the Earth's surface and looking at pollution in the lowest part of the atmosphere, we use two general radiation sources, because after all, a satellite sits here and it picks up radiation coming up from the Earth's surface. We can look at reflected sunlight coming down through the Earth's surface, bouncing off layers in the atmosphere or off the Earth's surface itself, and then coming up into to the satellite. And this generally happens in the shorter wavelengths, in the UV and the visible and the near infrared. Or we can look in the thermal infrared wavelengths, and we can look at emissions from the Earth's surface itself and from the different atmospheric layers. And there we look at the emissions according to the Planck function according to the temperature of the Earth's atmosphere, and we pick up signals according to that. And so here's an example of the transmission spectrum in the infrared, and you can see we have these characteristic signatures of all the different things that we might want to measure: water vapor, ozone, carbon dioxide, water vapor again, etc. And we have these absorptions according to the vibrational and rotational spectra of the particular gases, which I'm not going to go into in this particular talk. So if we want to be able to do some retrievals with this data, then we have to be able to understand the radiative transfer processes as the radiation passes through the atmosphere. That means understanding absorption and emission and scattering radiative processes through the atmosphere, and being able to embody that in a radiative transfer model to tell us what's happening. Okay, so some of the current assets that we've got satellites that we've got flying in the atmosphere at the moment that can tell us about atmospheric composition, and some of the ones that are coming up in a few years' time. In the US, we've gone through what might be called a golden age of satellite remote sensing of the atmosphere for atmospheric composition, and we've had 3 satellites called the Earth Observing System satellites, and they've been the Terra, Aqua, and the Aura satellites, and these have all carried sensors that are very useful for looking at the atmosphere, looking at different species, be it ozone or carbon monoxide or NO2 and things like this. In Europe, they've had another series of satellites, the METOP series, and these these continue to carry 2 instruments which are very useful: EASI, which I'll talk about a little bit in this talk, and the GOME-2 instrument. In the US, coming up, we might have some useful measurements from the CRIS instrument on the NPP satellite, and looking further forward into the future, we'll have the Sentinel-5 precursor mission, TROPOMI, which Peter Nellerveld will talk about after this. And then, of course, we can go into geostationary orbit, and we'll have 3 satellites, which will be very interesting because they'll add geostationary information to these low Earth orbit measurements later on. We'll have the TEMPO mission, and we have the PI of that, Dr. Kelly Chance here from the US, GEMS, and Dr. June Kim is PI of that, obviously, and then we have the European Sentinel-4 mission with two sensors which will be useful for atmospheric composition. So how do we do a retrieval? We've talked about having this remote sensing. We're remote sensing this radiation that comes up through the atmosphere. When we measure that, how do we actually do a retrieval? So these are the only equations I'm going to give you this afternoon, so you're very lucky. But I'm going to just show you in graphical terms how we do the retrieval. So we have to say, first of all, what do we want to measure? We have a required atmospheric parameter, we'll call that X, and that could be the profile of a particular trace gas in the atmosphere. And we have some new observations. We have an observation of the radiance at the top of the atmosphere, and also, very importantly, we have to know about what are the errors associated with that measurement. And usually, in order to be able to do a good retrieval using this information, we want some auxiliary information. We usually want meteorological fields of temperature and humidity and things like that. We often need to know something about the cloud fields, and so we probably take that from a different sensor or from our own sensor if it's able to give us that information. And usually we want to know something about the surface, because we're often, as I mentioned before, we're looking at reflected solar radiation from the Earth's surface, so that obviously depends on the reflectance. Or it could be the emission of the Earth's surface, and that depends on the emission, the emissivity of the Earth's surface. So these are auxiliary information that we really need to add to our satellite observations to be able to do a retrieval. Now, it so happens, and if you were at Dr. Jean-Lou's talk this morning, he explained in detail why this on its own is not sufficient in order to be able to do a retrieval. It's an under-constrained problem. There are many, many solutions to coming up with what the value of x is given these values here. So we have to add in a little bit of information to constrain the solution. So we add in what we think we already know about the atmosphere. So we think we understand how the atmosphere works, and we have a forward model, which basically tells us what we think that this satellite would measure in terms of a modeled radiance here, given all the processes that I talked about before, the scattering, the absorption, the emission of the atmosphere, which is embodied in our forward model here, if we had a particular state of the atmosphere X here. And we also have the measurement sensitivity. We have to know how we expect this radiance here to vary according to changes in this parameter that we want to measure. And that's embodied in this quantity that we call the weighting function, the Jacobian, which tells us basically the sensitivity of our measurement to the thing we want to measure. And again, we have to know what the errors are on this forward model and on our uncertainties on what we know. Well, that even then isn't sufficient in order to be able to constrain this problem. We have to add in some extra information, what we think might be close to the solution of the thing we want, and that's our a priori data. And again, that's what we think the atmosphere might look like. So this is our best guess of what this might look like in the atmosphere, along with the errors, the variation that we know from past experience, the variations and the covariances that we expect this parameter to have in the atmosphere. So we stick all these things together and we essentially minimize a cost function. That cost function, we do it in an optimal way to come up with an optimal estimate of x, and it's the optimal estimate of x given this particular constraint, the new radiances we've got, and also the things that we know about, that we think we know about the atmosphere here. And that comes out with a new example, a new estimate of what our retrieved quantity is, and also a very important thing is the averaging kernel. This tells us what the sensitivity of our retrieval, our new estimate of the of what the particular parameter is that we want to have. What is the relationship between this and the reality in the atmosphere? So this basically tells us how much of the information that goes into our new retrieval actually comes from the atmosphere itself. And again, we need to know all the errors. So just a little bit more information about the averaging kernels, since I'm going to come back to this later on in this talk and talk a little bit about them again. They're very important. They tell us, as I mentioned, they represent the retrieved profile sensitivity to the true profile. And so they tell us basically where our information comes from in the measurement. Where the information comes from in the retrieval. So here's an example from the MOPIT instrument, which measures carbon monoxide in the atmosphere. And this is showing different retrievals for different layers. Well, you can look here, for instance, this blue line the red line is the retrieval for the surface layer. But you can see here it's very small at the surface, and in fact it peaks up here and further up in the atmosphere. So this really tells me that although I think I'm trying to do a retrieval of the information at the surface, that the information in my measurement is not really coming from the surface. It's coming from about 700 hectopascals or 600 hectopascals or thereabouts. And so this is very important information. So it tells you really where the information in your measurement is coming from. And this is very important if we want to try and understand our measurements. And also later on, I'll talk about how we try and add in information down here at the bottom of the atmosphere. Okay, just a little light relief, some examples of pollutants that we can retrieve. And this will just be a few pretty pictures. And you might have seen some of these before. Tropospheric NO2. This is an important gas. It's a precursor to the formation of ozone in the lowest part of the atmosphere. And it's a very short-lived gas. It has a lifetime of a few hours, and basically it doesn't really get out of the lowest part of the atmosphere, the planetary boundary layer. So what this means is, because it doesn't get very far away from its sources, if we look at it from space, then we can really pick out the different source regions very easily. And you can see here all the different cities being picked out very nicely. This is also just an interesting slide that has got a lot of play. It's looking at rest days around the world. So we know that certainly in the Western Hemisphere, we all have a rest on Sunday. We don't go to work on Sunday. And so, as I mentioned, NO2 is a good indication of pollution close to the sources, and it comes from everything from urban activity, from transport and things like this. And so, not surprisingly, if you look at an average of the amount of NO2 as a function of day in the week, we get a dip on a Sunday because there are less emissions on those days. The same in the US and the same in Europe, it's on Sunday. If you go to the Middle East, the dip's on a Saturday because that's when the Muslim Sabbath is, and it's on a Friday, sorry, and then in Jerusalem, it's on a Saturday because that's when the Jewish Sabbath is. So it's a good indication of the sensitivity to these measurements have to the sources and the short time variation that we can pick up on these. Here's an example of shipping nitrogen dioxide, and we get nitrogen dioxide is given out by ships in their plumes as they burn oil to propel them around the globe, and you can pick out different ship tracks here. As ships come down through here and up into the Red Sea, there's large shipping lanes here. So here's another interesting example. If you pay attention to this little dot there, you can see there was a shift between those two time periods, and that was just to avoid that was to avoid the Somalian pirate activity that was around this area. The ships changed their courses to avoid that, and we could detect that from space. So another gas that we're very interested in is methane. This one's very important because it's involved in chemistry-climate interactions. It's one of the major gases it's a major pollutant of the atmosphere. It's also a precursor of tropospheric ozone, but it's also intimately involved as a greenhouse gas. It's the most important greenhouse gas after carbon dioxide, and in fact it has a greater global warming potential than carbon dioxide does. It's got a lot of interest in the last few years because if we consider the next 20 years or so, then probably regulating methane is the way that we could reduce reduce global warming more than trying to regulate carbon dioxide, for instance. So here's a nice plot. This is from the EASI instrument, which flies on the METOP satellite in Europe. And this shows you this what we call flying carpet figures here. This is a function of month during the year, and you can see we get greater concentrations in the northern hemisphere where some of the sources are strongest. We get the sources include activity, industrial activity, and things like that, but also wetlands, thawing permafrost, and different anthropogenic sources. For instance, like we get from keeping cows. Cows' flatulence from cows is, in fact, a big source of methane. It has a lifetime of about 8 to 10 years, depending, and this leads to very good mixing through the atmosphere. So if something is around for this length of time, then it means that we have quite a lot of it in the atmosphere, and then any single source that comes along afterwards forms a very small perturbation on what's already there. And that makes it very difficult to measure. So it means that if we want to measure this thing, if we want to measure methane, we have to have high precision in our measurements. And this consequently means that we usually do a lot of averaging in order to be able to get an idea of what the methane distribution looks like. And here's an example from the Skiamaki measurements over the US, but this took several years in which to produce. You can see sort of activity, anthropogenic activity in these areas, over LA, for instance. But it would be very nice in the future, especially as an indication of potential global warming and climate change, if we could have measurements of methane a bit more often. Tropospheric ozone. This is another gas, obviously, which is very related to atmospheric air quality. This is a toxic secondary pollutant, as I mentioned. It's formed from mixing of NOx and volatile organic carbons and CO and things like that. And the oxidation of these chemicals in the presence of the NOx forms tropospheric ozone. This is ozone down near the surface, not up in the stratosphere. We want it up in the stratosphere because that's where it protects us from ultraviolet light. We don't want it down in the lowest part of the atmosphere because that's where we get photochemical smog. Here's a nice picture again from the EASI experiment showing this is in January of 2011, and it's showing high concentrations of tropospheric ozone in the northern hemisphere here. And some of this is ozone that comes down from the stratosphere, and some of it's that's produced by human activity on the Earth's surface. You can also see this large plume out here. That's due to biomass burning, and I'll come back to that in a minute. Aerosols. We can see aerosols in the atmosphere and smoke. Here's an example. This is over the US, and this is from the MODIS instrument, which flies on the Terra satellite. And you can see clouds. This is a visible image, and you can see the clouds here, but you can also see this nice plume of smoke from fires that comes down here. And so taking an image like this, you can do some retrievals of that and turn it into a measure of what the optical depth is. This tells us how much particulate matter is in the total column as we look down towards the Earth. And there's been a lot of work trying to relate how we use these total column measurements of aerosol and try and relate that to what's going on at the surface. Because with aerosol, we have definitely ways that we can get an idea of what's happening through the full extent of the atmosphere, but we don't really. It's very hard to get measurements of actually what's happening at the surface, where we really wanted to know what it is for air quality. So that's a big field of research at the moment. Carbon monoxide. This is a gas that's really good for tracking pollution. It lasts for about a couple of months in the atmosphere. Depends on the season and the location. And unlike methane, which is around for 10 years and therefore becomes evenly mixed, and any one new source is a small perturbation on the background, in the case of carbon monoxide, we have it's only around for 2 months before it gets oxidized and by OH, the hydroxyl radical, and cleaned out of the atmosphere. And this means that any single new source can create a large perturbation on the background and makes it somewhat easier to measure. So we can often get perturbations on the background of about 100% or so, and it makes it very good for seeing sources and also for then tracking where the pollution goes after that. So in this particular case, what I'm showing here, these are wildfires in Arizona here, but they produced pollution in the form of carbon monoxide, which came out into the atmosphere and passed all over these states here. And then they commingled there with industrial emissions of carbon monoxide over here, because we get carbon monoxide produced whenever we have incomplete combustion. So anytime there's any kind of a fire or combustion in an internal combustion engine in a car or something like this, we get carbon monoxide produced along with carbon dioxide. So it's a very useful thing to measure as a tracer for the pollution that we are interested in. Here's a global map of carbon monoxide showing the distribution, the global distribution in March. And you can see here that we have a large amount of carbon monoxide in the northern part of the globe in the early part of the year, and this is due to the fact that there's very little photochemistry going on during the early part of the year, and during this time the carbon monoxide builds up in this part. But we can also see some source regions, for instance here in Asia, over China, due to industrial activity. Down here in Vietnam, some of these are fires. And these are fires here as well in sub-Saharan Africa. And if we move on to later on in the year, this is now in September, and this is after photochemistry has become very much more active in the atmosphere, and it's cleaned out the northern part of the atmosphere here. Most of the carbon monoxide that built up during the winter has been destroyed by the OH, and some of the sources are a bit more clear now. We've got wildfires in North America. We've still got industrial pollution here in China, but you can see at this time, look at this huge amount of pollution that wraps around the world from biomass burning in Africa and in South America. And so that's a very big source of pollution in the southern hemisphere. And if we look at, we can look at a zonal plot as a function of time, and we get this repeated pattern every year of high carbon monoxide, high pollution levels in the northern hemisphere in the springtime, in the January, February, March time frame, and then due to the biomass burning in the southern hemisphere, we see this high levels that we see in September or so. So we get this repeated pattern every year, but there are differences. And in fact, we could take out the repeating seasonal pattern here and just look at the anomalies from the regular seasonal pattern, and you'd be left with a plot that looked like this. And if we look at this, in fact, after that we can associate most of these anomalies with big fires. West African fires here, big fires in Russia in the late part of 2003, huge fires in Siberia in 2004. These are some of the biggest fires that we've seen during the 10-year lifetime of Moppet. Indonesia, and now it's interesting here, Indonesia dries out whenever there's an El Nino year. The weather patterns result in reduced rainfall over Indonesia, and then everything dries out, and then we get these large fires, which can be seen here in these Indonesian years. South Africa and China, the fires in China and Central America. So nearly all of these anomalies that we see are due to fires. So fire is a really important source of pollutants into the atmosphere. And I'll talk a little bit about this in the next section. This is pollutant emissions and transport. So fire as a pollutant source, we get approximately 500 million hectares of natural and human-induced biomass burning occurs each year. And this is a plot that we get from the MODIS instrument, looking down, and it uses basically thermal anomalies in order to be able to pick up hot spots and to see when when fire activity is taking place. And in that last plot I showed you, I mentioned that we had very big fires in Siberia in 2003. Well, they were picked up here in this MODIS plot here. In the south of Lake Baikal, there was a huge amount of burning activity, and this actually burnt some peat deposits, which produced all that carbon monoxide pollution. So here's an indication of the global reach of some of this fire pollution. This is again carbon monoxide from the Moppet instrument, and these were from Alaska wildfires in 2004. And you can see that the plume from these fires came down over the North America, over the eastern part of the North America, over Washington D.C. and that area, and then came out over the Atlantic Ocean and went all the way to Europe and impacted the air quality as far away as Europe. And when we have these kind of measurements, we can use them in conjunction with a chemical transport model, and we can use these measurements to adjust the concentrations in the model and also see what the implications are for other species that we're not measuring. So we can use these measurements to try and tell us something about, for instance, what the tropospheric ozone is happening. What's happening to the tropospheric ozone. And so these fires, in fact, the emissions from these fires using the measurements from MOPIC and putting it into a model, told us that it produced a change in the tropospheric ozone concentration on the east coast of the US by about as much as 25%. And it changed the ozone in Europe by about as much as 10%. So that's one of the things we can do with these kind of measurements. We can infer things about other species that we're not measuring directly by measurements that we are making when we use a chemical transport model as an intermediary. Here's a little example, more recent, of 2010, of fires in Moscow, which were very huge fires on the outskirts of Moscow, which really reduced air quality within the city, and this is right in the town centre. And here's a little movie from IAZI showing the build-up of, this is carbon monoxide again from IAZI, showing, and this, you can see these huge amounts of pollution that came out of this fire region around here, and you can see the extent that it got moved around the world. So it's quite a long, quite a lengthy impact. Other things we can measure, other specific sources, volcanic emissions. What can we measure in terms of volcanic emissions? Well, the IAZI instrument measures spectra for quite a few things. SO2, which comes out of volcanoes and can be transformed into sulfate aerosol. Ash. Ash is very dangerous for aviation, and it has a spectral signature here in the infrared, which allows us, in fact, we can, as I'll show in the next slide, we can actually tell what kind of ash it is. Hydrogen sulfide and sulfuric acid as well are other things we can measure. So here's, this is IAZI detection of volcanic ash from just 3 different volcanoes in a period of May and June of 2011. The Grimsvötn volcano in Iceland, that was here. You can see the extent to which this ash cloud moved. The Nabro in Eritrea, and Puihui in Chile here. And you can see this ash cloud moving along. Now, because of the different spectral signatures, we can actually say what kind of ash it is here. This, for instance, this one, there was a lot of ice produced out of the Nabro volcano, whereas the others were basalt and silica-rich and silica-poor ashes of various kinds. Ashes, as I mentioned, is very dangerous for aviation, and this is from the, I never can pronounce the name of this volcano in Iceland, but the volcano in Iceland that went up in 2010. And you can see these indications of ash cloud that came out of here and out over Europe, and this pretty much shut down air traffic in Europe for about a week or so. And now, for instance, the IAZI team are producing this as a product, as a quick look product of where ash is coming from, and they're supplying that to aviation authorities within Europe, so that they can have that and make better, more informed decisions about whether to ground aircraft or let them fly, etc. So that's it's an example in which some of the data that we're making is finding its way into applications. Urban pollution. There's a picture over China. On this screen, you can hardly see anything, but it's showing the very low air quality. And you can see here's an indication of, again, this is a MOPIT image of carbon monoxide, showing the large amount of urban pollution coming out of urban and industrial pollution out of out of China here. But what I really want to focus on is the extent to which this gets moved across the Atlantic here and makes landfall in the US. And so definitely, of course, as you know, this is passing over Korea on its way, and so this pollution has a long range impact, and I'll talk about long range impact in a minute. Another thing, as I mentioned, by putting these measurements into chemical transport models, we can also make inferences about other species as well. And there's been a lot of work that's been done looking at the case of the natural experiment that happened in the atmosphere when the Chinese authorities reduced traffic for the Olympics in 2008. And so here's the Beijing area and the CO loading over that area in 2007, and here's the corresponding picture in 2008. And there's been a lot of similar measurements done and illustrations of this using NO2 and other gases as well. So we know that this pollution, we were able to take this reduction in pollution from space. But if we put these estimates of the reduced pollution into chemical transport models, we have a lot of information about the correlations that exist, say, between carbon monoxide that is produced at the same time as carbon dioxide when we have combustion sources. So it tells us it's a way that we can get, without making measurements of carbon dioxide directly, we can get an estimate, knowing the reduction in carbon monoxide, we can come up with an estimate of what the reduction in carbon dioxide was. So how important is this long-range transport? There was a UN task force on this called HTAP, the Hemispheric Transport of Air Pollution, and it produced a report in 2010 to try and quantify, look at all the different evidence and see what was how important is intercontinental transport for affecting air quality. So these are some of the conclusions out of that report. There's plenty of observational evidence that ozone and particulate matter concentrations are in one particular region are influenced by intercontinental transport, and we're beginning to understand some of the mechanisms by which this happens. Nearly always, the biggest contribution to the local air quality is from emissions in the local vicinity, but just occasionally we have quite significant perturbations on top of that, which come from ozone and things that are actually produced due to emissions of precursors to ozone that came from a long distance away. And in fact, there was a conclusion out of this study that said that if all the areas outside of the US, for instance, decreased their perturbations by reduced their precursor emissions of ozone by about 20%, it would have about the same effect as if in the US itself it reduced it reduced the emissions by a comparable amount. So this means, what it really means is that it's very difficult in the US at the moment. There are so many air quality restrictions, it's very difficult to reduce some of these precursor emissions any further. And so the suggestion here would be that the US government would actually do better to go to somewhere like China and help the Chinese reduce their air pollution emissions rather than concentrate on what was happening in the US. So it's an interesting consequence of this, that where you might put your money in trying to improve your air quality. Here's a little movie. What this is showing is looking at the ozone in this part of the atmosphere here over North America, but it's looking at the sensitivity of the production of this ozone to emissions of NOx in other regions. So definitely the ozone in this region is sensitive to the production of NOx in that area itself, but you can see here it's also sensitive to the production of NOx in China and in some other areas of Asia. Again, actually, the movie is just coming to an end. Maybe it'll start again. No, it's not going to start again, so I'll move on from that. But that was basically just a way to show that we can do inverse modeling of when we have observations. We can put them into a model and then see what the implications are for not only for the thing that we're measuring, but for the gases that led to the production of that particular gas. So if long-range transport's an important thing, then we need to be able to quantify it a little bit closer. So what this movie here is showing is the concentration of carbon monoxide at the surface resulting from emissions or input into this particular area here in these two altitude ranges. So what this is showing is that this is the concentration at the surface that is due to emissions or production of carbon monoxide from the surface up to 4 kilometers. And this is showing the contribution at the surface that's actually due to inflow that's coming in from about 4 kilometers to 8 kilometers. And so you can see, in fact, both of these you add these together and you get what the total concentration is at the surface, but you can see a lot of the what we get at the surface actually came in much higher up in the atmosphere. So that tells us that we really have to understand what is the inflow from this long-range transport higher up in the atmosphere. And if we were going to be able to do this, this really means that we need to be able to separate what is local production of pollution from the long-range transport of pollution that was probably produced quite some distance away. This is over the US, so this is probably production out over Asia. So this means really, since this is coming in at 4 to 8 kilometers and this is towards the surface, we really want to be able to, in our satellite measurements, say something about the vertical distribution in order to be able to separate these two components when we do our analysis. And so that'll move on to this next section, which is improving the vertical sensitivity. So going back to radiative transfer just for a minute, I'm going to talk about multispectral remote sensing. So we said right in the beginning that we have two sources of radiation that we can pick up at our satellite. We can look at reflected solar radiation here, bouncing off the Earth's surface and then coming back up to the satellite. Or we can look at thermal emission from the Earth's surface and from the atmosphere, again reaching the satellite. The radiative transfer processes for both of these two different components to the radiation that we pick up here in the two different wavelengths, in the short wave at 2.3 microns and the longer wavelengths in the thermal infrared at 4.6 microns, they have different processes, radiative processes in the atmosphere determining their emission, absorption, scattering, etc. As I talked about before. And we can use these different processes to tell us something, to use this to our benefit, because they not only have different processes, but they have different, because these processes take place at different altitudes in the atmosphere, we can use this information to try and tell us something about the measurement sensitivity to those different altitudes. So here's, in the case of the solar reflectance here, this is showing that what this is, this straight line here, which is showing the change in the signal that we would expect at the satellite here due to a change in the mixing ratio of, say, carbon monoxide throughout this profile. And it's basically saying that if we change the mixing ratio at any point through this altitude, it'll have the same, pretty much the same sensitivity when we get to the satellite. So we have a full column retrieval here with pretty much uniform sensitivity. If we go into the infrared, the situation is somewhat different. In this particular case, we're seeing in the infrared that we have greater sensitivity to the changes in the mixing ratio of the gas we want to measure in the middle part of the atmosphere. And so what it would mean really, theoretically, is if we retrieved a partial column of the carbon monoxide using this measurement over this region, and we subtract it from a total column measurement in this region, we would be left with some information about what was happening close to the surface. And this is, in fact, what happens. I've come back to showing you some averaging kernels, and this is showing some multispectral retrieval averaging kernels and some comparison with Mosaic aircraft data. This is Moppet retrievals compared to the aircraft data. So just concentrate on this black line here, which is our surface retrieval, and you can see, in fact, in this particular case, we get a retrieval that peaks towards the surface, and we have sensitivity towards the surface. So that tells us we really are getting some good information about what's happening in the lowest part of the atmosphere. And in this particular case, the retrieval from satellite captures pretty well the profile as measured by an aircraft. This is a profile near New Delhi, and we pick up this large excursion in carbon monoxide in the lowest part of the atmosphere. Here's a picture over Asia, and as I mentioned, the thermal infrared measurement only is sensitive pretty much to what's happening higher up in the atmosphere. And in this particular case, if we did a retrieval just using that one signal, we don't really get very much information about what's happening lower down in the atmosphere. However, if we do the multispectral retrieval and we add in the information that we get from both of these signals, both in the thermal infrared and the near infrared, then we can start to pick out the different source regions. There's different cities here. You can even see Seoul here, slightly elevated concentrations here. So this provides us a way to really get, for the first time, some independent estimate of what the concentration of the pollution is right down near the surface. This is also being done for ozone, and this is some work this was some work that was done for the GeoCade project. And what this is showing is essentially the similar thing, that's showing averaging kernels. And if you look at the red line, it's showing that if you do retrievals in the UV, the VIS, the mid-infrared or the thermal infrared, with those single signals on their own, you don't get very good sensitivity towards the surface. However, if you mix it up and do a multispectral retrieval with the UV VIS plus UV TIR, or mix them all up together, then you can start to get much better sensitivity to actually what's happening right down near the surface. And this is one of the things that the TEMPO mission is going to do a lot of work on, and Zhonglu has been doing a lot of work on this. He's going to try and use the UV and the VIS signals together to try and get an enhanced measure of the ozone in the lowest part of the troposphere. Okay, trends and validation. I'm doing all right? 2 minutes? All right, I'll just go through this and I'll skip the last bit. Okay, I just want to talk about trends and validation just very quickly. It's very important when you have a satellite instrument that you go and do some comparisons with some other measurements. And this is what I'm showing on this plot is some comparisons of carbon monoxide from MOPIT with a FTS, that's a Fourier transform spectrometer, from Wollongong, that's near Sydney in Australia. And you can see here we have this seasonal cycle, and it's picked up very nicely by both the MOPIT and the Fourier transform instrument. And you can see that as I mentioned, the seasonal cycle, and the seasonal cycle in the southern hemisphere, if you remember before, is driven by the biomass burning. The peak is due to the biomass burning that we get every September and October from Africa and South America, and that really impacts the air quality over Australia. However, we can take away the seasonal cycle here and just look at the anomalies, and certain anomalies really stick out. And again, in the large scale context, these are usually due to fires that we can pick up in both the the local data from the FTIR, this is a single ground-based measurement, and from the satellite. They both pick up these large-scale fires. And here's an example of one of those fires over Canberra here, producing large amounts of smoke and carbon monoxide and other pollutants that came out over the Sydney region. It not only came out over the Sydney region, but then extended all over, out over the Indian Ocean towards New Zealand and even further along there. So the satellite data are very useful to give us this large-scale context. However, it's also interesting if we compare what we get from the satellite data, which gives us the large-scale context, but are not very good at picking up very small-scale pollution. If we compare that with the FTIR again, and look at the cases where we get pollution anomalies in the ground-based data, which is not picked up by the satellite. So this is an indication that the satellite was insensitive to these because they were too small. However, the local emissions, the local measurements picked them up. And Wollongong happens to have a big steelworks nearby, and often some of these local pollution events are picked up by their local FTS. So this is an indication. If you just had this FTIR data on its own, you really wouldn't know whether to choose these anomalies as being due to large-scale fires or the local pollution. But by mixing it up with the satellite data, we can try and distinguish these two different events. I'll skip this one in the interest of time. And we've talked before about trends as revealed by NO2. And we've got quite a few years of data now. This is the trend from GOME Skiamaki and now GOME 2 over China. And you can see this rising amount of pollution. And there's been quite a lot of work done on this and trying to see to what extent in different regions of the world the pollution has been going up or it's been going down. Over Asia, it's been going up, and over Europe and parts of America, it's definitely been going down, as revealed by the NO2 measurements. If we get a similar plot, if we look at the carbon monoxide loading, this is an interesting plot looking at the records of carbon monoxide year by year from 4 different instruments here: MOPIT, AIRS, TESS, and YASI. And you can see they all pretty much get the seasonal variation. But if we take out the usual seasonal variation and just look at the long-term trend, you can see that there's been this gradual decrease in the loading of carbon monoxide in the atmosphere over the last decade. And in fact, this carries on a previous work from ground-based stations that showed that it was about a decrease about 1% per year in the atmosphere over this period. And as Peter Nelvelt showed yesterday, as shown in the OMI data, we can see this economic downturn in about 2008, 2009. It's not really a trend through here, it's pretty much a step. There was a much less economic activity and industrial activity during this time, and that resulted in a reduction in the global loading of carbon monoxide. And I think, in the interest of time, since Professor Kim is telling me to be quiet, then I think I'll stop at that point, and I'll just move. You miss a really nice movie, but never mind. So just to the conclusions. With the last 10 years have really been exciting, and have provided some amazing pictures of pollutants in the troposphere from space. And we're now in a position to be able to look at this pollution from a wide variety of sources and emissions, and also examine tropospheric chemistry and the connection to climate. And especially when we mix this with chemical transport models and chemical data assimilation, we're able to tell a lot about a lot of different chemicals in the atmosphere that we can't measure from space. So we're at the point now where we have a lot of information that tell us about what's happening on a fairly large spatial scales, from continental to global, weekly to seasonal time scales. And of course, as we're here in this particular conference this week, the next step is to go to geostationary orbit and use instruments like GEMS and TEMPO and the Sentinel-4 to be able to really look at pollution in the lowest part of the atmosphere at high temporal resolution every hour and a high spatial resolution. So that's the exciting thing that's coming in for you folks later on. Thanks.
If you have a short question, we can take one. David is working at NCAR. You know, it's 미국의 국립대기과학연구소 지구 시스템 연구소 부소장을 맡고 계세요. 여러분들 선배님들도 많이 가 계시고. For the interest of time, we can go to the video.
Absolutely.
Thank you very much.
Okay.
David.